So our next speaker is Ganxiang, who is going to introduce this properly named framework called Quasar that applies equality saturation to optimize quantum circuits.
I'm Ganxiang from Columbia University. Today, I'm going to present our work, Quasar. Can you give me a... Yes, Raun. Okay. Check. Okay. So today, I'm going to present our work, equality saturation for quantum circuit optimization. This is a joint work with Paige Raun and Runzhou from University of Maryland and Ronghui from both Columbia University and CertiK. So our project is primarily focusing on optimizing quantum circuits, which are composed by a sequence of quantum gates operating on a set of quantum qubits. And the motivation here is that why we need to optimize a quantum circuit is that every quantum gate carry noises, which means that when we are running a quantum circuit over a real-world quantum hardware, each gate is subject to error and may produce incorrect results. So therefore, the more quantum gates that the circuits that we run for on the hardware, then the higher probability that we can get an incorrect answer. So the optimization objective for us is to minimize the number of the noisy gates over the whole circuit while preserving the functional equivalence between the original quantum circuit and the optimized ones. Therefore, we can maximize the correction rate about each quantum circuit of the quantum algorithm. That namely improves the quantum circuit fidelity. And the most advanced and the most widely used quantum circuit optimization method for now is a circuit rewrite. That is a pattern matching and a substitution to pattern match a sub-circuit inside the to-be optimized circuit and substitute with another one. And this is quite similar and with the people optimization in classical program optimization. So here is a few examples here. For example, the CNOT gate cancellation rewrite rule will cancel two adjacent CNOT gate into an empty circuit, and the rotation merge rule will merge two adjacent rotation gates into only one and accumulating their phases. And there are also some commutation rules to rewrite and reorder two adjacent NOT gates or the CNOT gates and to reorder their position in the gate sequence. So having seen the rewrite as the primary optimization results, the next question is that how optimizers apply those rewrites. And we found that this is not a trivial question, and this will later will limit the capability of optimization in the quantum circuit optimization. So we do a survey and classify most of the quantum optimizers into two categories. The first is the heuristic-based industry-level quantum compilers, including the QSKit and TKit. They manually crafted a carefully designed small set of rewrites, including tens or even hundreds of rewrites, and they apply those rewrites in an empirically designed rewrite sequence or a greedy function or a greedy algorithm. And another type is a search-based algorithm, mostly in the state of the art and in the recent years, including the Quasar, and Quark. Instead of using heuristics, they leverage the super optimization idea based on the classical optimizations to automatically synthesize a large size of rewrites composing thousands, tens of thousands, or even millions of rewrites. And then iteratively apply those rewrites selectively. In each iteration, they will apply only one single rewrite, and this rewrite is selected from such a large rewrite rule set with coupled with a specific search algorithm, such as the beam search, the simulated annealing, or the reinforcement learning. However, the question is that no matter what optimizer they are, and no matter what search algorithms that they use, no matter they are heuristics or the search-based, all of them apply those rewrites sequentially. So what does it mean by sequential? Sequential means that the rewrite just takes the output about the previous rewrite as its next rewrite as its own input, and to do that iteratively. So what's the problem with the sequential? So let's use an example to show how the sequential can lead to the suboptimality during the circuit optimization. So this is a real-world quantum circuit example, and this is a correct optimization path. We can see that it's composed by 4 sequential rewrites from T1 to the T4, and in each rewrite it will do a transformation. However, in the real-world optimization case, we are not that always so lucky to pick such a correct optimization path. For example, what if the optimizer can apply the rewrite T3 here? And this is not that rare, because in each iteration and each rewrite rule application, we have thousands, tens of thousands, and millions of rewrites that can be picked. And if that transformation was applied instead of T2, then it will. And so in that case, we are not that lucky and will get stuck, because after transformation, there is no possible pattern match that we can find with the current or coupled rewrite rule set. So therefore, the optimizer found that there is no pattern match found. So therefore, we can the whole optimization got stuck, and so no further improvement yet. So this phenomenon that the order that we apply those optimization can influence the final optimization result is not a fresh result. It's a well-studied problem called the phase ordering problem, studied by the Leverett et al. In 1979. Although this phase ordering problem has been well-studied and meditated in classical program optimization, we found that since all the quantum optimizers previously applied those optimization in a sequential manner, so the phase ordering problem limits their capability and remains to be unsolved. Therefore, we present Quasar, equality saturation for quantum circuit optimization. First, it handles the suboptimality caused by the phase ordering problem and other root causes by using equality saturation and leverage E-graph to represent and to do the exploration. And second, it proposed a series of optimizations to both reduce the circuit rewrite redundancy during exploration and also improve the E-graph scalability on the circuits. Finally, our evaluation shows that Quasar stands for the best optimizer across all the optimization times and all the possible metrics, and over 100 circuits that our benchmark included. And this figure shows the overview about the Quasar equalization. And I suppose all of you have been quite familiar with this equalizations. And so it's just a brief talk. It's just a brief representation that each input circuit are represented into the E-graph, and we do the rewrite to explore all the E-graph and finally do the extraction. So here, first, it will do initialization to the E-graph, and for simplicity here, we just represent the quantum circuit as the sequences and encode them into the E-graph. And for the paper, it have multiple encoding approaches. So it will first encode the input circuit 1 into the E-graph, and to explore in the exploration, it will do multiple rewrites. For example, here, circuit 2 rewrite will do a C0 gate and NOT gate commutation and store such a intermediate optimization result into the exploration and put them into the same classes with the original one. And then it will do a NOT gate cancellation that is matched with the circuit 2 variant stored in the E-graph. And this variant, circuit 3, will also be stored into the E-graph. Finally, it will do extraction under the user-specific cost model. And in this case, the best circuit is obvious, is definitely the circuit 3, because it has the least number of the noisy gates. That is, it only includes a C0 gate. And so it drops the circuit 1 and circuit 2. And given that extraction result of the E classes and E nodes, it will reconstruct the final output circuit. However, there are a few challenges for equality saturation to apply to the quantum circuit. It's driven us to develop a series of optimization, both offline and online. So due to the time limit, I will only discuss about the offline optimization and leave the online optimization works for the scalability issues to the paper. So the offline, major challenge is that we found that there are so many rewrites that we can apply during the equality saturation, and this prevents us from achieving valid optimization results before running out of resources. We can see that many previous work has exploited powerful rewrites, including the Quasar, Quasar, and Gawk. They include tens of thousands of rewrites, and if we just apply them naively to directly apply all of them to the graph, and even after 10 iterations, it will run out of memory and about 100 gigabytes of memory, and cannot generate any valid results in about 2 hours in most of the circuits. So the bottleneck is about the e-matching, right? We are applying so many distinct rewrites simultaneously to the e-graph. This pattern matching will indeed cost a lot. So our insight here is that although these rewrites are exploited by those sequential optimizers, they are powerful, they are useful, but they are not that necessary to include all of them in the equality saturation scenario. They are composable and redundant in the e-graph case. And even better, we can find atomic rewrites that are small enough, that are orthogonal and non-redundant, and will at the same time preserve the optimization capability as strong as the original large rewrite set. For example, this is a 3-qubit and 5 quantum gates rewrite, and we can find its reduced quantum gate from 5 to 2, and actually it can be decomposed into 3 distinct and smaller atomic rewrites that are composable, include a smaller number of the gates and the qubits. So how can we find that one? So a rewrite is composable and redundant under a rewrite set R, as we previously discussed, can be, as long as it can be composed by a sequence of combination of sequential rewrites from the left-hand side term to the right-hand side term. And we found that finding such atomic rewrites can also be done by leveraging equality saturation. Given a left-hand side term, we can apply a currently we found atomic rewrite to saturate such a left-hand side term. And if the right-hand side term is also be found in the E-class, then that means we can find a equivalence combination of the rewrite trace from the left-hand side to the right-hand side. Therefore, this rewrite can be safely reduced without any degrade about the optimization capability. And if that's not found, this atomic rewrite can be added to the current atomic rewrite set. By leveraging this technique, we have squeezed the rewrite over tens of thousands into just exactly 40, and this is a pre-processing offline optimization to achieve that. So as previously discussed, we only talk about only one optimization, and we will jump to the evaluation. We learn about 40 atomic rewrites, and we evaluate our Quasar optimization results over 176 algorithms with over the IBM Eagle gated set with the newest quantum parameters. Our evaluation shows that Quasar is the best optimizer across all the optimization times, which means that, as shown in the figure, that with the x-axis to be the optimization time, we allow each optimizer to run from 1 minute to over 2 hours. And the y-axis represents the gate reduction rate as a metric for reevaluating the optimization quality. The higher the better. We found that as shown in the orange line, the Quasar can dominate all the can find the best results across all the benchmarks after we left him run up to 1 minute, and it will dominate all the optimization results. Furthermore, we found that Quasar is not only the best optimizer on all the times, but also on all the metrics. We evaluate Quasar on 4 metrics that all the previous optimizers evaluated, including CNOT gate reduction rate, total gate reduction rate, fidelity, and circuit depth. And most importantly, it can beat QSKIT in over 100% in the CNOT gate reduction rate. And in general, it can mostly find a better solution over 80% of the circuits than all the others. And we also show that compared to the other rewrite rule sets, the atomic rewrite rule set is the best set that can be the fastest and can have the best optimization quality. Okay, so time to summarize. we present Quasar equality separation for quantum circuit optimization. It foresolves the sequential optimizer suboptimality challenge caused by the phase order problem by introducing equality separation on the graphs over the circuit. And it also reduced the rewrite rule redundancy during the exploration by introducing an offline atomic rewrite rule inference, also by equality separation. And also, in our paper, we also discussed the scalability of equality separation over the quantum circuit by introducing two solutions. So one is the equality separation-based solution called scheduled equality separation, and another is a quantum-driven solution called ILP-based reordering to use the integer linear programming to reorder the gate sequences, thereby reduce the efforts in the exploration. And in total, it is the best optimizer for now across all the metrics and all the bugs. Thank you. Quasar is open source, and please scan the code to try it out. And I'm happy to take any questions. Thank you.
Okay, we have time for 3 questions.
Hi, thanks for the good talk. So most equality saturation domains don't, at least, they don't have so many rewrites. And in your case, you minimize it to a smaller set. But why are there so many rewrites, at least to start with, in this domain?
Oh, you mean the initial rewrite set about
the one that was.
Yeah, we will. This is because the rewrites are the term of the equation comparing of the left-hand side term, left-hand circuit and right-hand circuit, right? And this equation can be generated by enumerating the possible combination about the atomic gates, and the initial equivalent checking can be done by linear algebra checking, because each quantum circuit can be represented as a linear algebra matrix. So, and therefore, and since that each rewrite set is not that big, it only includes several qubits, and each terms include several less than 10 quantum gates. So that comparison over the matrix is not that big. Its cost is low. Okay, thank you.
Hi, thanks for the talk. So my understanding is that in quantum, there are often rewrites that can be applied with some probability. And in this case, as far as I understand, like all the rewrites are
unconditional.
Unconditional. So I'm kind of curious if you think that egraphs can be used to apply these probabilistic rules.
These probabilistic-based rewrite rules are also including the resynthesis-based quantum optimizers that I do not discuss in this paper, and these are considered as an orthogonal work to apply those probabilistic-based rewriting and the quantum resynthesis and integrated into the Quasar. Yeah, and we are expected this to be a future extension to our Quasar work. Thank you.
Great talk. There's a well-known complete equational theory by Andre Clement and co-authors for quantum circuits, and I believe that that's under 50 equations, probably on the order of 25, though you can correct me if I'm wrong. Did you try plugging in that set of equations into the egraph tool, and was this better?
Sorry, excuse me. Which rewrite rule set?
There's a few papers, but there's a paper by Andre Clement and Simon Perdis and others that is a complete equational theory for quantum circuits. So that should get you from any quantum circuit to an equivalent one. And I believe it's under 40 rewrite rules, so I haven't counted them. So I was just wondering if you tried plugging in any of the results from those papers into the egraph tool and wanted to see whether or not you could get better results.
I think we can do such an evaluation to evaluate the quality about the Clemens et al.'s rewrite rule set comparing to our atomic rewrite rule sets in future. Thank you.
Okay.
Okay, let's thank Ganxiang again.
Cool.